Hi, I'm Michael Chatlani. I'm the Vice President of Business Development at L3 Harris's Montreal operation for our power systems and simulation business. I'm here with my friend and colleague, Benoit Montpetit. For short, I call him Ben, as you will see. We're going to talk to you today about an innovative molten salt reactor design and how we are applying simulation to assist in the engineering of that new design nuclear power plant. So I'll kick it off with an introduction, then I'll hand it over to Ben, and he's going to talk to you about what kind of updates that we had to make to our technology to accommodate a novel reactor like this, and how did we go about configuring a molten salt reactor. He'll also talk to you about the current status of the program, and then I'll come back on and wrap it up for you. So by way of introduction, let's just talk about small modular reactors in general. They are defined as nuclear reactors with power between 10 megawatts electric and 300 megawatts electric. So from micro modular reactors to grid scale reactors of 300 megawatts electric. These are often integral and modular, and they're designed for factory fabrication. There are a number of designs that are emerging in the marketplace. Water-cooled reactors, like our conventional ones, high-temperature gas-cooled, fast neutron spectrum, molten salt, and micro-modular reactors. The global market size is estimated by Pillsbury at $150 billion between 2025 and 2040. We actually see a larger market potential for SMRs. Ben and I are both based in Montreal, Canada, and Canada actually happens to be a front runner in the deployment of small modular reactors. Our regulator, the Canadian Nuclear Safety Commission, is conducting pre-licensing vendor design reviews, or what is called VDRs, for 10 different designs, and 2 more VDR agreements are under development. For today's discussion, simulation, we're going to be talking about it in the context of initial design and verification support and testing. And that's what we call simulation assisted engineering. But, you know, simulation obviously has a very large role to play in training as well. The program that we will be focusing on is actually a molten salt reactor. It's produced by terrestrial energy. The name of the plant is the IMSR, or Integral Molten Salt Reactor, and we'll give you a lot more information. A synopsis on the IMSR plant is that it's a Generation 4 molten salt technology that's thermally very stable, and it operates at both high temperature and low pressure. The 700 degrees high temperature operation means that the plant will result in 44% thermal efficiency. That is much higher than conventional nuclear power plants that are operating today. The low pressure also means that the engineering complexity and the cost of deploying such plants will be lower. The molten salt coolant and molten salt fuel combined results in a walkaway safe nuclear power plant. It is the only Generation 4 SMR plant that is designed to use standard enrichment fuel. So less than 5% enrichment, which means that that fuel is readily available. It's a 195 megawatt electric plant, which is deemed to be a good size for today's market. It's also designed for fast modular construction. It's going to be deployed in 4 years. The commercial results resulting from the high temperature and low pressure operation are important for this design. There's going to, you know, of course, we have the inherent and passive safety, the smaller size and the modularity, but the reactor itself and the way it's designed is going to really drive down the levelized cost of electricity for this plant. The levelized cost of electricity, or what we call the LCOE, for electric power markets will be under $50 per megawatt hour. For industrial heat markets, the in-furnace cost of heat will be less than $6 per millions of BTUs. Terrestrial energy, like us, is based in Canada, and they are specifically in Oakville, Ontario. They are one of the front runners that is being considered by Ontario Power Generation to put an IMSR at the Darlington site in Ontario. So obviously today's discussion is about simulation, and we're going to be talking about simulation for the most part. But just to put this in context, for an operating plant, when we are creating an operating training simulator, we start with very well-established plant data. So it's fairly straightforward for us to deploy these simulators. But in today's example with the IMSR, what we're talking about is a new plant design that is evolving. And we want to make that simulation available to assist in that evolving plant design. So with all these moving parts, moving information, I should say, it's a challenging task. So simulation assisted engineering has a lot of value, right? As I said before, simulators are not only for training, but as we continuously evolve the simulation at the system level, we join systems together, it becomes a plant model, and changes are constantly occurring as the design is maturing. We have tools that make it possible for us to rapidly prototype or rapidly change the simulation. And this is great for achieving various verification and validation as the design is maturing. And then several other things can be done with the simulation. Ultimately, what we're aiming for is, as this product matures, as the plant matures, then what we will ultimately have is the foundation for the full scope operator training simulators, which will be used by the operators of the IMSR plants. And so that's why we call the product durable, and that means that we're never throwing away what we're working on. It's always got a long-term purpose. Now, the environment that we use to model these plants and the IMSR specifically is called ORCID. And there's two main components within ORCID that I'll be talking about: ORCID Core Builder and ORCID Modeling Environment. We'll come to that. ORCID as a whole is an integrated environment that brings together all of the plant simulation in a high fidelity, real-time power plant model, both for simulation assisted engineering and for operator training simulators. We are using only these tools that I mentioned, ORCID Core Builder and ORCID Modeling Environment. And so that is unique in the industry, that only two tools are being used to model an entire nuclear power plant. ORCID Core Builder generates what we call Comet Plus, which is the full three-dimensional two-energy group neutronics model, which uses the nodal expansion method. It is used for both the design of the reactor core model and the offline calculations. ORCID Modeling Environment is a drag, drop, connect simulation environment, as you see in the blue boxes across the top of the screen. It generates non-homogeneous two-phase models, which we call Anthem, room models for containment and whatnot, homogeneous two-phase models for other balanced plant systems, electrical and INC models, and it's also got the runtime component to see what is happening from the Comet Plus model. And of course, it includes interfaces to external systems. And what we might mean by that is we might be connecting to other software, third-party software, other hardware interfaces for the simulator. So we have all those capabilities to connect to those external systems from ORCID modeling environment. It's an intuitive graphical development, test, and runtime environment with built-in configuration management, which is especially important when you're working on new design plant that is evolving. And of course, it's all, as you can see, through a graphical user interface, which makes it easy for our engineers and for our customers and partners to rapidly go in and change the model and see what it does. Today's focus is going to be mostly on the Comet Plus reactor core model and the non-homogeneous two-phase models known as Anthem, and the homogeneous two-phase models that are generated with these tools. Ben, over to you.
Okay, so let's continue with the simulation technology updates and configuring molten salt reactor plant model. So here we have an IMSR flow diagram with this model implementation. So just to summarize, in blue, we have the fuel salt flowing inside the graphite moderator, where most of the nuclear power is generated. And then that heat is carried up to the primary heat exchanger and transferred to the coolant salt in green. And then through the secondary heat exchanger, transferred to the solar cell in yellow. And finally, it gets released into the steam generator to produce steam that will be used by the balance of plant to generate electricity. So all these salt circuit and the steam generator are all modeled with the non-homogeneous two-phase model that we call Anthem. The balance of plant is modeled with the homogeneous two-phase model that we also call hydraulic model. And all the neutronic calculation are performed by the neutronic model called Comet Plus. And next. So the IMSR simulation assist engineering project scope consists of three configuration delivery. The first configuration include the Anthem thermohydraulic model, so the reactor vessel, yard vessel, including Anthem update for steam generator and liquid salt, and also the point kinetic reactor model to interface with Anthem. The second configuration consists of the first configuration plus the addition of the balance of plant model to provide dynamic boundary condition to the IMSR steam generator, and also the addition of the emergency heat removal system. For the configuration number 3, this is the configuration we're working on currently. We have the goal to replace the point kinetic model with the Comet Plus multi-nodal neutronic model to interface with Anthem. In parallel with those configurations, L3 Harris has offered ORCID technology and training to terrestrial energy. So the following slide will show the different input required to update technology and configure plant model. In other words, everything we need to build that IMSR simulator. So first, we have the L3 Harris foundational technology update, such as additional delay neutron group, update of neutron scattering, considering liquid fuel, liquid phase to include salt, incorporate salt property, and additional heat transfer and friction correlation. We will talk more about all these topics in the following slide. Also, it is important to get the right geometric data, such as detailed construction drawing, elevation, pin ID, heat exchanger dimension, and any other spatial component. And of course, operational condition to calibrate that simulator to the right conditions, such as pressure, temperature, flow, heat and mass balance, pump, dynamic head, flow rate and speed, heat exchanger, heat load, and reactor thermal power. So reactor design and ORCID core builder updates. The IMSR involves fuel within fluoride coolant cell moving inside the vessel, integral reactor core with graphite moderator, and neutrons, mainly in thermal spectrum. The following figure is simply a just a reminder of the 3 neutron energy group that we have in a nuclear reactor. So that new reactor design in terms of simulation raised some question. What is the impact of having non-static uranium in core model? How do we deal with decayed product and delay neutron if they are moving in core? Are 6 group of delay neutrons sufficient for this type of core? Or 2 neutron energy groups sufficient to model this type of core? And what core nodization is required? So first, there is Serpent-2, that is a Monte Carlo reactor burn-up physics calculation code that was used to produce required data processed by ORCID core builder, such as reference data, perturbation data, and validation data. That leads to ORCID core builder updates. First, the core builder was updated to read and process data from Serpent-2. Since Serpent-2 data set were already homogenized into 2 energy groups, the data could be used as is without any modification related to energy group. Preliminary result revealed that L3 high-risk Comet Plus need to include upscattering. That means from thermal neutron going back to the fast energy spectrum. Also, there was the need to add addition of 2 more delay neutron group. And given Serpent-2 is not a nodal model, ORCID core builder could not extract core nodization from design data, as it usually does. So ORCID core builder was updated to easily read user-defined nodization. Now, model implementation for liquid fuel or moving fuel. Modeling liquid fuel for IMSR instead of solid fuels model for conventional nuclear power plants require reevaluation of reactor and thermohydraulic model implementation interface. Certain calculations handled by Comet Plus need to be transferred to NTEM to accommodate fuel movement. So on the left, we have a table for modeling implementation and interface for a typical nuclear power plant such as a PWR. And on the right, the same table, but for an IMSR. So as you can see, the decay heat, xenon iodine concentration, and delay neutron calculation were moved from Comet Plus to NTEM for the IMSR to take into account flow, which is already calculated properly in NTEM. Now, incorporating liquid salt in NTEM. So for conventional reactor, the vapor phase in NTEM is water vapor and non-condensable, and the liquid phase was simply liquid water. No other type of liquid was ever considered. Water properties calculate from thin table, and non-condensable property come from well-defined correlation. Now, to incorporate salt within NTEM, it doesn't change much on the vapor phase, but for liquid phase, not only liquid water is considered now, but all these different liquid salt. So liquid can be water or molten salt, and the salt property come from different experimental correlation. So salt data and correlation considered for NTEM update are the salt composition, thermal conductivity, viscosity, specificity, and density. With all these properties, NTEM is able to model accurately all the thermohydraulic of molten salt. Next. Also, other NTEM updates were done for heat exchanger. Indeed, this IMSR design involved many different heat exchanger for primary heat exchanger, secondary heat exchanger, emergency heat exchanger, steam generator, and reactor that differ from conventional nuclear power plant steam generator model in the past. So additional heat transfer and friction correlation were added to NTEM, for example, cross-flow outside tube, and improved non-condensable modeling for heat transfer application, such as below 0 degree condition. Following all these updates to the technology and model of L3 Harris, here the current status of our work as of today. So the IMSR simulation work performed today. Started work on IMSR development with goal to update ORCID core builder and core model, adapt and update NTEM object and code to use molten salt, develop and integrate IMSR simulation model. With data and assistance from terrestrial energy, ORCID-based IMSR simulation was great, based on that flow diagram and this model implementation. So first, of course, ORCID core builder was was updated to read Serpent2 data to generate input from Comet Plus. In addition, ORCID modeling environment with NTEM was used to develop all the following systems, such as the reactor vessel, fuel salt loop, coolant salt loop, solar salt loop, steam generators and all its components, and the emergency heat removal system. Also, ORCID modeling environment and the homogeneous two-phase model was used to develop the full balance of plant model, including steam, turbine, generator, and feed water system. So the IMSR simulation involved the following: establish heat transfer between loop and perform flow and pressure calculations, replicate heat balance from Thermoflex heat balance software, include new heat transfer and friction correlation, use control emulation to replicate terrestrial energy control philosophy, integrate real-time Comet Plus and NTEM models, using point kinetic reactor core model as a steering step, and then finalizing multi-nodal reactor core model integration. Compare and comparing L3 Iris simulation result with terrestrial energy FlowNext simulation environment result. So here on the right, we have the core design nodalization that we have in ORCID Core Builder. And from an automated process, we homogenize this nodalization into a real-time nodalization that can be used with the real-time version of Comet. Below, we have some sample ORCID modeling environment schematic where we see a real-time model for steam and turbine system and feed water system. Preliminary model result, starting with ORCID Core Builder Comet Plus. So ORCID Core Builder used to run static flux solution based on neutronic source data from Serpent2 and determine core nodalization. Adjustment were needed and implement, such as improving nodalization and include upscattering. This greatly improved the result, but there's still work ongoing for further improvement. Work continues to finalize implementation of real-time multinodal Comet Plus neutronic model and integration with NTEM. In meantime, to continue overall project implementation and testing, include a point kinetic model with reactivity coefficient from Serpent2. Point kinetic model allow dynamic flux power response based on fuel cell temperature and density change and graphite temperature change. The point kinetic model calculates fission power, and decayed power is calculated by NTEM. On ORCID modeling environment and is two different models, NTEM and hydraulic. Steady state tests and power maneuver tests were run, and the results were compared with terrestrial FlowNext simulation. In general, there's a good agreement with the result of both simulator, but there's still work ongoing to improve the behavior of the L3 Iris simulator. For comparison with FlowNext simulation, L3 Iris ORCID-based simulation was run with NTEM salt circuit as generator, homogeneous two-phase hydraulic BOP system, point kinetic reactor core model, and control emulator. It is important to note that there's some difference between the FlowNext and ORCID simulation. For example, control logic in simulations are at different maturity level and not the same. Control design work is still ongoing. Solar salt and steam generator configuration is different. L3 Iris model need to be updated with final design. And there's some difference in evaporator and BOP model implementation. Knowing all this difference will help a lot. Knowing this difference will help a lot to identify area of improvement for the L3 Iris simulator.
Thanks, Ben.
Welcome.
So just to bring it all to a close, so we have very high expectations for the penetration of small modular reactors in the market to effectively fight climate change. We are pleased to be collaborating with Terrestrial Energy. It's been a relatively short relationship, but a very productive and even fun relationship. The simulation to support this new IMSR plant design, SAE, is also going to form the basis of the future operator training simulators for this plant. The technology, ORCID, that has been described by Ben, needed to be updated to take into account molten salt reactor properties that we hadn't considered in previous projects. The reactor core, the salt circuits, the steam generators, and the BOP have all been modeled and integrated. Although, as Ben mentioned, we are still using the point kinetics model until the multinodal model is ready to put in. We have been delivering interim configurations to terrestrial energy to work with the simulation. And the simulation results are tracking the expected results. So we're looking good. Until the end of 2021, we plan to do further model updates as Ben has described, and we will be rolling out the full IMSR configuration number 3 to terrestrial energy with the multinodal reactor model. The continued use of our technology, the ORCID technology, and the simulated IMSR will go on to test and verify design changes and to incorporate and validate the plant control systems as they become available. With that, Ben and I want to thank you very much for your attention, and we wish you a wonderful conference.